Hey there, TouchDesigner developers. Jack DiLaura here with the Interactive and Immersive HQ. In this video, we're going to take a look at the first new operator family to TouchDesigner in almost 20 years, POPs or point operators. POPs are GPU-based operators that create and manipulate 3D data. They offer a number of performance and functional benefits over the previous SOP family, and are a very exciting addition to the program. We're going to dive into some very surface level basics in this video and just cover some sort of initial steps of what's going on with this new operator family, and then sort of set ourselves up for some more advanced examples to come. So we're going to start off with a very simple example today with just a couple of POPs and some operators to kind of showcase the data that they contain. So one thing to know about POPs right off the bat is that they contain, as is probably obvious, a set of points, but they also contain a set of attributes. And attributes can be things like point position, a normal vector, maybe texture coordinates, or as in this case, I'm actually applying a color attribute to each one of the points within this sphere pop. But we can also create custom attributes as well. Attributes can be applied to the points themselves, or as we'll look at in some later examples, some different aspects like something like the primitives that make up the shape. In this first example, we're just going to focus on attributes that have been applied to the points. So over here on the right, we've got a popViewer component, which is something that will be included in the palette. And it is a very handy tool for visualizing the different attributes that are contained within your pop geometry. So again, this should look pretty familiar. We've got a typical TouchDesigner 3D viewer situation, but as you can see, our shape looks a little bit different than the simple sphere that we saw over here in our network. So we can see a couple of things right away. We've got our points are highlighted, and we can kind of figure out the point position based on these little white dots. We also have these larger circles around each point that shows the color attribute specifically that is applied to each point. And then we have some red arrows which point outwards from every single point that makes up this sphere. And those are showcasing our point normals. Along with that, we can see the underlying primitives that make up our sphere geometry, which are triangles. So the popViewer gives us a very flexible tool set for visualizing different aspects of our geometry. And we can toggle on and off any number of these different components, like these arrows or these color circles or little dots that showcase the points. We can also choose which attribute is being visualized for some, not all, but some of these components. So for example, the red arrows here are showcasing the normals currently, but I could also showcase maybe the point position as a vector if I wanted to, or if I had any custom attributes, I could also visualize those as well. At the bottom, we have the ability to play around with some rendering options like the shading or wireframe that is being shown in our viewer. As you can see, this is a very useful tool to have in our toolbox, and definitely something that will come in handy, especially as things get more complex working with POPs. So I'm going to head back to the network now, and we're going to dive into the three DATs below this POP network. So another thing to know about POPs is that we have not only a set of points, but we have three separate lists of information. So we've got a point list, we've got a vertex list, and we have a primitive list. And we'll take a look at what these look like in practice now. So we've got pop2 DATs that are converting or grabbing that information from my sphere above, and this is our point list. This will look familiar if you've ever taken SOP geometry and converted it into DAT form. We've got an index column, then we've got point positions, we've got our color attribute, we've also got our normal attribute over here on the right. Something I want to point out here is that this is, of course, updating in real time as the values assigned to the color attribute change. And depending on the number of attributes that you have assigned to your specific geometry, like, for example, if I say removed this color attribute, you may have more or less columns in this list. So as soon as I bypassed that noise pop, that disappeared from my list, and now I only have the point position attribute and the normal vector attribute. Cool. So we're going to head straight over to the primitive list over here on the right. And this one is a little bit more straightforward, I guess, because there's less to look at. And I guess I can't really get that to scale up as much as I'd like, but hopefully you can see that there. We've got, again, an index column to reference the primitives independently. We've got our primitive type column in the center, and as expected, these are all triangles, which we saw already in our popViewer. And then we have the vertices column, which is a list that showcases the corresponding points in our point list that are the vertices that make up that particular primitive, or that the primitive contains. So, for example, if I look at this index value 1, and we go over to the vertices column, we can see vertices 4, 3, and 1. That would correspond to, in our point list, point index 4, point index 3, and point index 1. So you can see how you can kind of cross-reference these different lists of information to get more information about certain aspects, whether that's the primitive, the point, or the vertex. Lastly, we'll have a look at our vertex list, and this is a quick moment to showcase that we can, as mentioned before, assign attributes to any one of these lists. And in this case, our texture coordinates have been assigned to the vertex list. So that's what the last three columns here are for. But we'll start over on the left. Our index, again, allows us to reference a specific vertex. In the middle, we have this interesting column which says primitive :v index. So this allows us to basically decipher which particular primitive we're looking at in our geometry by the first digit. And then the second digit is the particular vertex within that primitive. So meaning if I went to, say, index number 8 here, that would be primitive number 2, and the third vertex or v-index of that particular primitive. On the right, we have the point index column, or p-index rather. And this is, again, another way to cross-reference back to our point list which specific point this vertex corresponds to. So for example, if I'm looking at index number 13 here, primitive 4, v-index 1, that is referencing p-index 6. So if I were to pull up my point list, here is index 6, and those are the XYZ coordinates for that particular point. So my point here is to show you the data that pops contain, and also to show you how these different sets of data kind of cross-reference one another. So again, I mentioned a moment ago that we can apply attributes to any one of our lists, our point list, our vertex list, our primitive list. And a great way to see this in practice is to take a look at the noise pop. So the noise pop allows us to choose where we want to apply our noise to. And as mentioned before, I've created a color attribute which I'm applying to our points. But I can choose, if I want to, with this attribute class parameter, to apply this to something else, like perhaps our primitives instead. And when I do that, I don't know if you saw the change there, we end up with a different result. So instead of just sort of a smooth surface, we now can see that each one of our triangle primitives has a solid color applied to it. So there are, different situations where this comes in handy. A lot of times you'll probably be applying attributes to points directly, especially if you get into things like particle movement. But it is very handy that we have this ability to kind of pick and choose where we want to apply our attributes. Next up, let's have a look at the primitive types. So from the top, we've got the point primitive type, which is a single point. So we've got here a circle pop, which has the connectivity turned to none, and thus is just producing a bunch of points in the sort of perimeter shape of the circle. And you can see over here, we've got the point type showing up in our pop2 list. And this is useful if, for example, you want to render just single points in your scene. After that, we have a line primitive type, which is going to require 2 points. So in this case, again, we've got the same circle, and we now have a connected perimeter, which looks like a single continuous line. It's made up of a bunch of small line segments, which again contain 2 points. Over here, we can see in our primitive list that we have the type of line, and now instead of just a single vertex, we have 2 vertices per primitive. Continuing right along, we have next line strips, and these can be 1 or more points. So in this case, we're actually starting off with a circle pop that has its primitive set to be triangles. We're then using a convert pop to change those triangles into line strips, and then are left with this sort of sliced up pie. As we can see over here on the right, we've got, again, line strip primitives, and we've got a number of vertices. What's cool about line strips, and kind of makes them a little bit more powerful than just simply a line, is that they can, as we can see here, contain more than just 2 points. And along with that, we can have open or closed line strips. So when we see that the last point in our vertex list here is the same as the first point, we know that this line strip is a closed line strip. And if the last point was not the same as the first, then it would be open. But what is great and powerful about this is that with just a single line strip primitive, we're able to create, essentially one of these slices of this pie, which would take, if we were to use lines, again, with 2 points each, 3 primitives to create that same shape. Next up, we've got the triangle primitive, which is going to require 3 points. We've already looked at this in our previous example, but here it is in grid form. And again, we've just got some simple triangular shapes making up that grid. Over here, we can see, again, the primitive type of triangle, and we have 3 vertices for that primitive. Lastly, we have the quads primitive type, which is going to require 4 points. So you can see here where we had triangles before, now we just have rectangular shapes. And again, over here in our list, we've got the quad primitive type along with 4 vertices per primitive. So those are the primitive types when it comes to pops. Now, one thing I want to point out is that we actually don't always need to have a primitive assigned to our pop geometry. And in fact, we can simply have a point list if we are, for example, using this information for instancing. In that case, the instancing setup is only going to look at the point list and doesn't really care about the primitives that are assigned. However, if you want to render that information into a scene, you will need to have some sort of primitive assigned. So we've got some options there, but hopefully this gives you a little bit of a better idea as to how primitives work with pops. As with the other operator families in TouchDesigner, the pop family contains generators and filters. Generators are going to create, in general, or maybe import the 3D data that we'll end up working with, and our filter operators tend to modify that data. So, for example, we'll pick one of the new operators in the family, the point generator pop. Well, I guess they're all new, but this one in specific is a little bit different than things we've seen in the past. So the point generator pop, it's almost like a combination of previous operators that existed as components, and or a little bit of the sprinkle SOP along with some basic geometry options. But regardless, it allows us to select a particular shape that we want to distribute points either within the volume of or on the surface of. And so I'm going to leave it with this basic sphere shape. I'm going to set my distribution on the surface, and you can see here we're generating a bunch of points randomly positioned around the surface of the sphere. I'll turn the random switch off there, and we can see now we've got some evenly spaced points, which gives us some interesting circular patterns. Likewise, if I wanted to filter this with something, maybe I could use the normalize pop, which is another new one, which has a bunch of ways that we can normalize the attributes of our pop geometry. And here I could maybe do something like use a lookup curve for the different axes of data, and in the end create something like this. So I've got this kind of three-dimensional box shape that I've used some math to create. So again, we've got our generators and our filters. So a common question about pops is whether or not they can be used in our typical rendering pipeline. And the answer is yes. They function much in the same way as the previous SOP family did, obviously offering some benefits of their own. But in this example that we have here, I've got a simple setup where I'm creating this kind of undulating noise shape with some pop geometry and then rendering that directly. So let's hop into the geo comp over here and just take a look. So here is my pop network, and sort of similar to examples you may have seen with SOPs, we have a sphere. The point positions are being manipulated by a noise pop. We have a sprinkle pop, which is sprinkling points over the surface of that shape. Next, we have the very cool new trail pop, which is giving us this sort of trailing effect as the points are moving around in space, and actually generates, now that we know about primitives, line strips when it is doing so, which is very cool. And then I've got my final null here, which has been set to display and render. So when I head back up a level in my project, that is then being rendered in my scene. So just like SOPs, we can, set up complex networks within and in conjunction with the geocomp for rendering. We can apply materials, etc. And as we will look at in the next example, we can also use this data for instancing. So here is a quick example showcasing instancing with pops. Here's a quick look at the output. So I've just got a sphere shape, which has some colors applied and is just sort of rotating around in space. So within the geo, I have just a simple box pop, which again is being displayed and rendered. And then if I head up a level back into this part of my project, we can see that I have a sphere pop, which is in the end being used for instancing. So I've got a normalized pop in between, which I'm using to basically, as input, take the point positions and then do a little bit of math to them and then apply that as a color attribute to the points, so that when I head back into the geocomp, I can use those color attributes that I've created and assign those to the instance colors. Likewise, the point positions of each one of the points in that sphere pop are being used as the translate positions for the instances. So again, we can use the attributes that we have created within our pop network to really create some very complicated and flexible instancing setups that can take full advantage of this new operator family. In this last example, we're going to take a look at some of the performance benefits that pops bring to the table. So being GPU-based, pops offer a much higher level of performance than was previously possible with the SOP family of operators. And we can look at this particular example and really see that in practice. So I've set up a very simple kind of pseudo particle system. We don't have the sort of typical particle attributes like life, or even anything beyond sort of applying forces to an initial set of particles. But regardless, we have a sphere that provides the initial positions for the particles. I've applied a bit of color to the particles, and then I'm using a feedback loop along with some forces that are being applied via a noise top and some math, or noise pop rather, and some math pops, and ending up generating something that looks like curl noise if we take a look at the final output. So this is cool, and looks pretty nice. But what is very interesting about this particular example, if I head back to the network for a second and middle mouse click on this null, is that I've got a total of 1 million points within this little system here, and I'm staying pretty close to 60 frames per second performance-wise, even as I'm doing this screen recording and all the other recording stuff that is going on with that. So it allows us to have a much higher count of particles in this case, and do all of this manipulation in real time within this pop network, and then render that out to our final output here. So obviously that is, many leaps and bounds beyond what was possible with the previous SOP family of operators, and is very exciting, as we dive into this new family and start to look for opportunities for experimentation. So with that, I hope this video has been an interesting and useful first look at this new family of operators. Obviously, there is a ton to cover with so many operators being added at once, and we will definitely be diving into all of that in the weeks and months to come. So stay tuned, and as always, thank you so much for watching. Looking forward to seeing you in the next video.
Hey folks, thanks for watching. If you like our YouTube content, I highly recommend you check out the Interactive and Immersive HQ Pro. The HQ Pro is the only comprehensive educational resource and community for immersive design, TouchDesigner, and creative tech pros. In the HQ Pro trainings, we cover almost any topic you can think of, and we go way more in depth than we do in our YouTube tutorials. We have a private group where Matthew Reagan, myself, and our other industry veteran and pioneer teachers answer your questions every single day. If that sounds cool, click the link in the description to learn more. And if you enjoyed this video, hit that like button, and don't forget to subscribe for more free TouchDesigner and immersive content.